Good afternoon, ladies and gentlemen. Welcome to the Popular Science Forum, Meet the Shaw Laureates, the challenges and the joy of doing science. The forum is about to begin. Please be seated. Today, the Hong Kong Science Museum and the Shaw Prize Foundations have the pleasure to present this event. Before the forum starts, we would like to invite both the organizers and the Shaw Laureates 2015 to take a few photos. May I invite our guests to come on to the stage. Shall we take some more photos with the laureates in the middle? Thank you very much. Please be seated. The forum is about to begin. May I invite Professor Kenneth Young, Vice Chairman, Board of Adjudicators of Shaw Prize, to give a brief introduction of the forum, as well as introducing the Shaw Laureates in Astronomy 2015. Professor Young, please.
Welcome to this science forum, Meet the Shaw Laureates 2015. And this event is organized by the Leisure and Cultural Services Department together with Shaw Prize Foundation. In case you don't know, the Shaw Prize was established in 2002 under the auspices of Mr. Run Run Shaw to honor individuals, regardless of race, nationality, gender, and religious belief, who have achieved significant breakthroughs in academic and scientific research or applications, and whose work has resulted in a positive and profound impact on mankind. There are 3 annual awards, as you can see, in astronomy, in life science and medicine, and in mathematical sciences. The 5 laureates this year were announced in June, and they received their awards in a ceremony on Thursday. That was just 2 days ago. Yesterday, they gave talks at 3 universities, and today we're delighted to have the 5 laureates here with us to talk to the public. Of course, about their work, but more precisely and more importantly, about the journey, the challenges and the joy of doing science. And I think you see that subtitle over there. Is doing science and research lonely and difficult? Or is it full of fun and amazement? Or is it full of fun and amazement because it is lonely and difficult? The Shaw Laureates will share their experience with the eager audience. We shall start with astronomy. The Shaw Prize in Astronomy 2015 was awarded to Mr. William J. Barocchi. Mr. Barocchi studied at Wisconsin and San Jose State in California. He is the principal investigator for the Kepler mission of NASA. He has worked at NASA Ames Research Center since 1962, quite a long time, on a variety of projects, including, for example, heat shields for the Apollo mission, lightning activity in planetary atmospheres, and modeling nitric oxides and CFCs in the ozone layer. Most recently, and when I say recently, that's over, I think, more than a decade, he has conceived, designed, and fought for the Kepler mission, which tries to look for planets going around stars, other stars than our sun in our galaxy. The method he proposed is conceptually simple and elegant, but technically very challenging, so much so that it was initially met with skepticism. The mission has achieved spectacular success. Over 1,000 such planets have now been confirmed, with 3 times as many others being candidates still being studied. By extrapolating beyond that sample, it is now generally believed that many, perhaps most stars have planets, including many planets at a distance such that the temperature would allow life to exist. This is a major step forward in trying to understand whether life exists at all elsewhere in the universe, not by speculation, but by evidence. Mr. Barocchi will now tell us about his quest, and I hope about the fun he has had along the way. Mr. Barocchi, please.
This first figure shows that once upon a time I was younger. The car is about the same age, as in the 30s. I'd like, first of all, to thank so much Professor Young and the distinguished guests here and the students, ladies and gentlemen. I'd like to talk a little bit about how my career evolved and some of the things that I did early that helped me ultimately attack the problem of how we find whether Earths around other stars are common or rare. It's important because, of course, if they are common, if they are often found in the habitable zone, then we might expect that there could be a lot of life in our galaxy, and that would help us as a step in exploring further our galaxy for life. It's a very expensive, difficult process, and so that step is really required so that we can go on and justify to our colleagues and to the community, to the people, that this exploration is worth the effort. But I want to start out and sort of show you how the different things that I did when I came to NASA Ames in 1962 ultimately came together to build that Kepler mission and get that result. When I came to Ames, there were a number of ways one could participate, one of which was to become a specialist in a particular area and accomplish things in that way. Another way was to come in and sort of as a project scientist. You came in, people gave you a problem, you worked on the problem, you learned enough about that to solve that problem, and you moved on through a series of problems as NASA problems and projects evolved. And I was part of the latter. So I'll show you sort of where I started and how that helped ultimately with the Kepler project. This is a little sketch of the timeline. So in 1962, I finished my Master's of Science degree at the University of Wisconsin, negotiated a job with NASA. I chose NASA in California versus that in Cleveland. Joined a team to develop stable spacecraft and to develop a heat shield for the Apollo mission. When you go to the moon, it's a much more difficult situation when you come back into the atmosphere. You're traveling much faster. The compressed gas is much hotter. The wake behind the spacecraft is much more intense. And so if you're going to keep the astronauts alive, you really need to understand that plasma and how it flows around the spacecraft and how much energy it gives to the spacecraft and how that affects the material boiling off of that heat shield. And it was quite a nice team to join because they had a very positive can-do attitude. No one had ever gone to the moon, but we were going to see to it that men would go to the moon and return safely. And so that attitude was a huge help in developing my career. I worked on spectral analysis of the shock layer. The shock heated gas in front of the spacecraft is hotter than that of the surface. That spacecraft is essentially immersed in something as hot as the sun. And so you've got to be sure you can keep the temperature where the astronauts are very, very cool. And the spectrum, of course, tells you about what's happening in that hot gas. We succeeded. We got to the moon. People came back safely, and it was time to move on. The team disbanded, and I joined a new group, and the group's objective was try to understand how the Earth's atmosphere, the ozone layer in particular, was being affected by what humans were doing, in particular what we were thinking about doing, and that was to develop a supersonic jet aircraft, and those jet aircraft would fly at very high altitudes. The nitric oxides they would make would catalytically affect those. It would destroy the ozone, and that nitric oxide would constantly be replenished. So we had to understand what the difficulty would be and how we might mitigate the problem. So we built mathematical models. Those mathematical models of what was happening would be I would ultimately use a similar approach to try to understand how we would use photometry to find planets, and how we would develop an instrument in such a fashion that we would get the maximum amount of science with the minimum amount of cost. One of the other things that I did and was actually interested in high school and college was on trying to understand lightning activity. Lightning activity has a lot of roles in the sorts of things that I did. One of which is, of course, the temperature in a lightning flash is hotter than that of a sun, hotter than that of the surface of most stars. You can observe it in the Earth's atmosphere. It occurs naturally. You don't have to make it. And so you can look at the spectrum, and you can say, that's the sort of spectrum I expect from the heat shield, in front of the heat shield, that shock layer. The books, the tables of atomic line probabilities and so on did not have all that. So we actually used the information from the lightning that we saw in the atmosphere and had been surveyed in several ways. It is also interesting in that it forms nitric oxides. It's the nitric oxides that have been formed for the beginning of our planet. Lightning occurs in water clouds that affects the ozone. And so if you're modeling the Earth's atmosphere, you need to understand the role that nitric oxide plays from lightning. Now today, of course, we overwhelm that with the kinds of oxides, the nitric oxides we produce in fertilizer. But it was an important problem. And when you think about it happening in other planets, the other planets have methane and other gases that could form pre-biological molecules. So a real importance there as well. The next item here is one of the things I recommend to people, that is go to seminars, learn as much as you can about as many things as you can. At NASA, we had seminars that talked about how do you find life on Mars? How could you find planets? And so that really inspired me to come up with a method to find Earth or Earth-sized planets. And so I started developing methods, photometric methods to find Earth-sized planets, looking at a star and seeing how it dimmed when a planet crossed in front of it, and using that information to determine the characteristics and frequency of planets. So the high-precision photometry that was required was to some extent based on what I had learned and what I had done on the Apollo program. The mathematical techniques that we used to calculate the trade-offs between how the instrument was selected and how it was optimized in terms of the size of the mirror, focal length, all these sorts of things were something that modeled, we called it the merit function model, helped us use. So in the 1983-2000 period, it's quite a few years, 17 years, I was working on developing the methods of photometry to detect exoplanets. We had to develop a photometer that was several hundred times, 500 times more precise than any instrument to do photometry that had ever been developed before. So the can-do attitude that I picked up from the Apollo program, again, was very useful here. You really had to believe this would work because there were a lot of dead ends, a lot of things that you did that simply failed, and you had to just keep on going. 1992, there was a program that NASA started where you had medium-sized missions. Instead of little tiny ones, the great big ones, something medium-sized that would be perfect to take a photometer in space and look for planets. And I wrote proposals so that I put together a team, and with the team, we wrote proposal after proposal, and it would be rejected again and again. And I'll show a little bit of that briefly, but ultimately we won through. We were able to get the funding from NASA to show it really would work and build that mission, launch that mission, and get the results that Professor Young talked about. And I became the principal investigator of that mission in 2001 through 2009. And in 2013, that mission was complete, and that basically we had finished the observations. We still have work to do to analyze that data. We are still finding planets in that data. But that data is available to everyone in the world. It's public. And so we find that many in the science community, even students, look at that data and they find planets that we have missed. So it's been a wonderful aspect of the mission. I'd like to show you a little bit about what's required when you talk about trying to take men to the moon and come back and keep them alive. This is a sketch of the light gas guns that are used to fire model vehicles at greater than the escape velocity in a lab and catch that vehicle So basically, these are two naval cannons from a battleship that are bolted together that use hydrogen and oxygen with some helium to drive a 100 kilogram parcel of gas through a supersonic nozzle down a test chamber, and a gun fires the model directly against that airstream. And together, you have more than escape speed. This is an example of such a model. It's a small pellet-like thing, and it's the material is being tested. How fast does it ablate away? How fast can it, or how long can it stand the tremendous heat that's here? This is the shock wave that's penetrating. It's evaporating and boiling off, and that material is flowing behind it, very, very hot, radiating to the back of that model. And we, of course, measure those aspects. It also, of course, wobbles back and forth, and that tells us about the stability of the shapes that we're using. The facility here, the test facility, is actually shown here. This is about 20 meters long, and these are the windows through which the instrumentation picks it up and determines how that wobble is going. Is it stabilizing? What's the radiation doing? Over here, we actually see a picture from a camera inside the test section looking at the gun blast here, and we see the model with its wake right here. This is the wake, and here, that bright, brilliant spot is that shock layer in front of the heat shield. So when you make these measurements, how long do you have to observe the spectra to get the temperature and the density of that plasma? You have a very long time if you measure time in nanoseconds. Let me talk a little bit about trying to understand lightning. When you look at lightning in the Earth's atmosphere, you see this sort of picture and spectra. And what you're seeing is the temperature so high that you're seeing ionized and excited atomic nitrogen, oxygen, and oxygen. And it's a pretty clean spectrum. Unless you look closely, you see there's some continuum radiation from the electrons interacting with the ions. If you say, I'd like to understand that in the lab, it's hard to do it in chasing it down, you get a spectrum that looks like this. It's terrible. You see some of the lines here, but you have thousands of lines that don't belong. And the problem here is that if you do this in a lab, you take high voltage from a capacitor, you put it across some electrodes, a spark occurs, you build a strong current, but what happens is the electrodes become so hot they eject supersonic streams of material into your plasma, your arc, and it's contaminated with all these lines. So the problem is all you need to do is generate lightning with no electrodes. And so that was quite a problem, but I was able with some of the facilities at Ames to try an idea, and that was to assume that if you take a strong laser beam and focus it down at some instant, at some position, you can say at that instant, in that position, all that energy is being carried by the electric field. The electric field at that point would then strip off the electrons and build that plasma. And so that, in fact, is what was done. This is the facility. It's just a little flask, a few centimeters in diameter. The laser here has a light that comes in, is focused with a lens inside, and whatever gas you put there is then in a millimeter size volume is at temperatures like 25,000 Kelvin, 10 atmospheres, 20 atmospheres. So it's a very nice simulation of lightning or the plasma, hot plasma in front of a reentry vehicle. And you can measure the photometry here. You could actually measure how much light comes out for how much energy you put in that plasma. And you can measure the spectra here as well and understand the state properties of this gas. The state properties of the gas in this case are not pressure and temperature, but they are in fact the line width of your atomic lines and the line ratios. And from those two state properties, you can deduce things like pressure and temperature. If you ask yourself, well, we have lightning on Earth, but is there lightning on other planets that might have pre-biological molecules made by lightning? And here's an example. Here's a picture of the dark side of Jupiter. We will never see that unless we go to take a spaceship and look from behind Jupiter. So this was, in fact, taken by one of the Voyager spacecraft. And you can see at low latitudes there's a stream of very bright spots, and at high latitude some more bright spots. They line up in latitude like that because that planet, the outside of the planet, is heated by the sun, and so lightning doesn't occur except at particular latitudes where the flux of the atmospheric circulation allows the heat from the interior of the planet to come out and form this lightning. Putting a latitude-longitude grid on a planet that's completely dark is quite a challenge in itself. I'd like to talk more about the Kepler project and the sorts of things that are required quite often in building a space project. Generally, a space mission is going to be doing something that hasn't been done before. And that means you're going to face technological challenges, you're going to face challenges of practicality, and often psychological challenges in terms of can you stand all the people saying no year after year. And so what we see here is a little timeline. In 1970, an idea was proposed by a fellow named Frank Rosenblatt that you might use photometry to look for planets around other stars by just looking at the dimming when a planet crossed in front of a star. Unfortunately, he died shortly thereafter. Not much happened for a long time. In the 80s, I read his paper, decided I could build a photometer that would do that job. It would be several hundred times more precise than other photometer ever built, and so I started on that, wrote a paper talking about the fact that it had to be outside the Earth's atmosphere, it had to have that kind of precision, and another paper talking about the fact that one of the limitations would be that even if we built the perfect photometer, the variability of stars, all stars, would actually make it difficult for us to find the smallest planets. I had a chance to go to various observatories, try their equipment out, talk to the scientists in the community about what I was trying to do, get some of their help, face some of their challenges. And in 1992, the Discovery mission started where we could propose our mission, our idea to NASA on a 2-year basis. Every 2 years we could propose. And we proposed in 1992, and they said, well, that's a great idea, but there are no detectors that can do the 10 part per million photometry that you want. And so part of our response was to actually work to show that CCD detectors, they didn't intrinsically have that kind of precision, but if you looked at their errors, the errors were systematic. You could measure the errors, you could correct for the errors, and now you could indeed do the job. Proposed again in 1994, and in 1994 they said, well, this is a space mission with our telescope. It'll cost $1 billion like the Hubble Space Telescope did, and so no, we won't fly your mission. The following year, however, was a wonderful discovery. That was 1995, and the first exoplanet was found with radial velocity from the ground. A Jupiter-like planet with a 4-day orbit, and that was a wonderful discovery because it proved there were planets around other stars other than just Earth. We proposed again in 1996 then, and they said, well, you're talking about building a photometer that doesn't do one star at a time like you do with ground-based systems, but instead you're talking about 10,000 or 100,000 stars at a time. So if you really believe you can do that, go out and build an observatory. Build a telescope. Show us it can be done. And our team did that. Our team borrowed a dome on an observatory. We built the telescopes. We got it to operate. We showed it could be done, and we published those results. So we were in time to do the next proposal in 1998. And we proposed here, and they said that, well, that's great that you've done all those things, but your proposal's rejected again. No one has ever shown you can do 10 parts per million with a system like a system that will be in orbit. A little telescope with a little star field, galactic cosmic rays passing through, the telescope jittering around, moving the image around. Show us that that can be done, and here's $500,000 to do that. $500,000 sounds like a lot, but it's half of what you need to do the job. And so I had to borrow the other $500,000, and I'm still worried that I haven't quite paid it back yet. We proposed again in 2000. It was also the year, for the first time, ground-based telescopes using transit photometry actually saw a planet, a Jupiter-like planet that had been discovered with radial velocity. But again, it's showing photometry now does work. You certainly can find giant planets. So another great happening. 2001, our proposal was accepted. We built the mission about 8-9 years, launched in 2009, operated for 4 years. We have found over 4,600 planetary candidates, have already confirmed 1,000 of those as definite planets. We expect to confirm the rest in the coming years, although it may take decades for some of the more difficult ones. So it's been a very successful mission. This is sort of a quick examples of what Professor Young showed. This is the size of the planet. Earth is 1, Neptune 4, Jupiter 11, and the orbital period. The Earth, of course, is an orbital period of 365 days. And here we're showing that yellow is the Kepler data, that almost all these planets are small planets. Planets the size of Earth, smaller than Earth, maybe somewhat larger than Earth. So the majority of these planets around other stars are small. And as Professor Young pointed out, we're finding that most stars have planets. Many of them are small planets, roughly the size of the Earth, and a fair fraction of those in the habitable zone. A fair fraction indicating that we have billions of planets that are small in the habitable zone and possibly have life. And that's encouraging to future missions, which will surpass Kepler in so many ways and look for the atmospheres of those planets. So let me conclude by saying it's been a wonderful career, quite a varied career, as I did different things to try to solve the kinds of problems that we at NASA were particularly concerned with. Thank you.
Thank you for sharing your inspiring ideas with us, Mr. Barocchi. Please take a seat here on the stage. The question and answer sections is about to begin. May I also invite Professor Young to take a seat on the stage and join the discussion.
Thank you again for a wonderful talk. I don't know whether you noticed, you were so focused on giving your talk, somebody up there arranged audio-visual effects for you while you were talking about lightning. Did you notice? No? Did you guys notice? Yeah. Yeah, somebody up there likes you. So perhaps we could invite questions from the audience. Yeah?
Somebody up there missed, though.
Yeah. Come on. I think the first thing about doing science is to be not afraid to ask questions. There are no dumb questions, right? Yes. There are occasionally dumb answers, but there's never a dumb question.
Excuse me, sorry. I have a question about the financing that you had to do for the test bed because you were only given $500,000, because that takes a lot of commitment to the work that you do to like seek out a loan for that, especially as NASA has been going through budget cuts and stuff. So I was just wondering, how much confidence did you have in yourself at that time? Like you talked about the can-do spirit, so I'm just curious about that.
If you don't have confidence in yourself, don't get into science. You really have to believe that what you're doing is worthwhile, worth your effort, and it's that commitment, your commitment to your science, to getting it done properly, that's just really required to do good science. And I, at that time, certainly had tremendous confidence in that what we were doing would succeed, it would make a valuable contribution. There were a lot of people that didn't have that confidence in our group, but you can't let that stop you. We were rejected time and time again. Carl Sagan was part of our group, and each time we would fail, I would ask the members, do you want to try again? I remember Carl Sagan saying yes, he wanted to try again. He felt the mission was worthwhile and that he, in fact, hoped he could be more active in promoting our mission. He unfortunately died shortly thereafter, but our team really worked and believed in this mission, and so they made it successful.
Thank you for your talk. Just as how you concluded your career as interesting and varied, I wonder if each step of you try to step out of your previous field a bit, do you find it challenging, or are there any struggles, or do you actively seek such a difference from your previous work and try to enrich your experience?
I think she was talking about the fact that the projects are different one from another and how they fit together. Is that correct?
Yeah, like the differences between your different projects. Is it how were that you actively seek different projects to do as challenges, or do you have any struggles when stepping a bit out of your previous projects?
Well, each of the different projects, of course, was quite different. Modeling the Earth's atmosphere is quite different from trying to understand plasma around an entry vehicle, and quite different from trying to build a highly precise photometer. But I think most people in science find all of science interesting, whether it's biology or plasmas or whatever it is. And those challenges, I think, are looked forward to. You learn so much from attacking new kinds of problems and learning about them and finding new colleagues and learning from them. So I think it's one of the privileges of being part of the science community when you have different projects. And in fact, I think if you look at people at universities, they will often move from one idea to another to better understand various areas of science. So it's a privilege and a challenge, of course, but a privilege.
You mentioned that you've discovered many planets which are happy for determining habitability. And also in the same slide, you mentioned something about Fermi something, and that is something I don't understand. Can you elaborate?
I'm missing the last part of his question.
Last part of the question was about the Fermi criteria.
Fermi paradox, yes. Well, what we have found is, of course, first of all, when we make those measurements, that's a sample. That's not the parent distribution. It's a sample distribution. But by making corrections to that, you can get an estimate of the parent distribution. The parent distribution said, essentially, on average, all stars, certainly most stars, have at least one planet, probably more than one. A good fraction of those are small, as we saw. Many of those are in a habitable zone. And so we're talking about billions of planets that are roughly Earth-sized in a habitable zone of their stars. And what do you make of that? Well, Fermi asked, well, if there are so much life in space, why haven't they contacted us? And so that comes to fore very directly now. We know that you can't dismiss that and say, well, there aren't any planets out there, not in the habitable zone. We know there are lots of planets and in the habitable zone. So the question you have to ask is, why haven't we heard from them? Why haven't they visited us? Why hasn't SETI picked up that signal if there are billions of planets out there? I don't know the answer, and I don't think any of us know the answer, although you can certainly speculate. Maybe our assumption is wrong, that if the conditions are right for life, maybe it doesn't start. Maybe we're very, very exceptional. Or maybe life just evolves to bacteria or to dinosaurs, which are rather non-technical kind of, group. They tended to eat little human beings at the time, so I don't have a lot of sympathy for them. But in any case, we don't know what the answer is. It's our children and our future generations are going to have to go way beyond what Kepler's done. Kepler was a probe. Are there planets out there? Are they Earth-sized? Are they in the habitable zone? The answer is yes. Do they have atmospheres? Kepler can't tell you whether any of them have atmospheres. The exception would be the Jupiters, the massive planets. But do those atmospheres have water vapor and CO2 that you need for life? Do they have oxygen representing maybe higher life? We don't know the answers to that. And if you built a mission to do that, you still wouldn't know whether there was life. You'd have to build a bigger system that might tell you whether you see color changes that would represent foliage changing from season to season. So Kepler is one step. There are many more steps. The Fermi paradox is something that we will need to think very seriously about. What is the meaning of what we have found and not found?
Questions?
Have you ever thought about the possibility of some astronomer, another Mr. Barocchi out there in one of the planets we are talking about, on their own Kepler mission, finding a habitable planet, third rock from the sun on the Orion spur, and asking why they haven't heard from us?
Our team includes an enormous range of people with talents, and it includes people from the SETI program. And one of the things they have looked into is the fact that every so often the planets that we look at line up in such a fashion they're looking directly at us and they could see a transit. That would be a time for SETI to be looking for a signal. In other words, if they are broadcasting television or something like that, we should see their signal, they would look for our signal. In fact, the SETI program turns their telescopes at each of these planets that we find, at each of these stars, looking for those signals. So we're very aware that there may be beings out there that may be looking at us. It's an important question, important possibility.
Do you think that the Earth has enough resources for us to find out other organisms in the space? Do the Earth have enough resources? Because if we put so much resources on finding other organisms in space, we will exhaust our other consumption. Thank you.
He's asking about the resources.
I think the question was, do we have enough resources to do this project and many others? Is that the question? I didn't quite catch the last bit.
Yes, okay. That's a marvelous question. It takes a surprisingly small amount of our resources to do this research, or any research, medical research, any of the kinds of research that are important to us. We have a huge amount of resources. The trick is to use our resources carefully. And in particular, something that really concerns me is that we pollute our atmosphere. And the destruction of our atmosphere means the destruction of ourselves. So we'll not do any research, we'll not do any breathing at some point. So it's important for us to look at the wonderful Earth that we have. There is no planet we can go to. We cannot go to the stars. Even at 10 times the speed of light, faster than Star Trek went, it would take centuries. And we can't even imagine going at the speed of light. So it's important that we really are careful with our resources and spend the effort necessary to protect our environment.
Okay, we have a few more minutes, just a few more. Any questions?
Hi, I have a question regarding a comment that you made about how the Kepler data was released to the public and that scientists and universities can access that. So my question is this unique to the Kepler program, or do other NASA projects share this kind of idea? And how has that contributed to the subsequent development of the program? Thank you.
I'm missing I have a hard time hearing.
Oh, the question was about the public availability of
Yes.
the Kepler data,
Oh,
and whether this policy is unique to Kepler or whether it's more general. Yeah.
There's certainly two aspects to that. When you spend years and years putting together a mission, you want to make sure your team has first opportunity to look at the data, to calibrate the data, maybe to write some of the papers that they need to develop their career. But ultimately, that data goes to the public. In the latter part of our mission, we've tried to get the data to the public as quickly as possible. And the mission, as it functions today, basically the data, as soon as it's calibrated, goes to the public, and the public makes those discoveries. They make making many of those discoveries today. And certainly, I don't know about all governments, but certainly in the United States, there's been a real emphasis to make sure the public gets that data as quickly as possible, and that we put in a public archive, and we put that data in the archive so anybody can use it with the tools to reduce the data, to analyze the data, to understand the instrument. So that's all there available to everyone, and has been certainly for the Kepler mission for a number of years now. And if you look in the literature, you'll see that many of the public, including students, use that data to find planets that we have missed. And it's something I think that we'll see more and more frequently.
Okay, perhaps one final question. If not, I have a written question submitted from somebody. Could I just read that out? As the Kepler is such a great tool of photometry, what are the new understandings of stellar activities and stellar physics that you have gained from this mission?
Again, another superb question. Kepler looks at 170,000 stars simultaneously to find planets, but it looks at 170,000 stars continuously. So it learns an enormous amount about these stars. It can actually, for stars that are when our star gets older, our sun gets older, it will expand. We'd like to know what's going to happen inside that star. How does it change? Well, there are stars that are older than our sun, and we can use Kepler data to look inside, see whether it's burning hydrogen, burning helium, how it's rotating, what size the stars are. So we learn a tremendous amount about stars like our sun, what our sun will become, but also stars quite different than ours. We see things that are extremely surprising. One of the things that really amazed us, in fact, was we saw what looked like a planet that crossed the star. We saw the light dip, come back up, and it was constant. And then when a planet goes around behind the star, you don't see any reflected light from it because it's hidden behind the star. Well, generally, the planet has so little light, you don't see it anyhow. But this one, when it went behind the star, the light from that object and the star went down dramatically, which was really a puzzle. But we knew how big the planet was because we'd measured the transit. We knew how much light decreased, so we knew the flux of light. So we knew its temperature. So the object that had gone behind that star, we could show, was hotter than the star. And that's sort of amazing. You think, well, is this object, which is hotter than the star, being heated by an object cooler than itself? That would be completely contrary to physics, contrary to thermodynamics. You say, well, no, this is a really unusual star, a white dwarf. But the white dwarf is small like the Earth, not big like Jupiter. So again, a real puzzle. We were able to try to understand it was a different kind of white dwarf. We found stars where the two, that instead of the signal going down, the signal went up. How could that be? How could the signal get stronger? We thought it might be an orbiting black hole, a microlensing event. And we looked with spectra and recognized it was equally strange. Two stars that were very far from one another come screaming toward each other and just missed colliding by the diameter of one star. And when two stars near each other that close, they're not spherical. They're football shaped, pointed at each other. And that increase in area gives you an increase in light. And similarly, they had waves. The light would go up and down as these stars oscillated up and down. All sorts of interesting things out there to discover. So if you're interested in astrophysics of stars, we have a lot of data for you.
Thank you very much, Mr. Barocchi, for the most interesting discussion.
I want to thank Mr. Barocchi again for a most interesting discussion. I think the bottom line is that there are lots of interesting phenomena for those who have perseverance and who are willing to build good instruments and who have the courage to go and look. Now we come to mathematics, right? So may I start by giving us a short introduction both to the subject and to our two speakers. The Shaw Prize in Mathematical Sciences for 2015 was awarded to Professor Gert Faltings and Professor Henryk Iwaniak for their contributions to number theory. Number theory is a surprisingly elegant and deep branch of mathematics, treasured for its beauty. Sometimes the public is too much concerned about what use it may have. In fact, when we held a press conference in June announcing the laureates, I was actually tempted to say that it has military applications in China. That would have made the press sit up. I refer to the Chinese remainder theorem, which to us is known as the 韩信点并问题, 韩信点并问题. It goes like this. I was talking to Professor Faltings just now, and he doesn't know the historical context, so I have to tell the story. So there was this General Han about 2,000 years ago. He was trying to count his soldiers. So he made them line up 3 in a row, and he found there was 1 left over. And then he made them line up 5 in a row, and still 1 left over. And then they made them line up 7 in a row, again, one left over. So how many soldiers did he have? And that's called the Chinese remainder theorem. And it has to do with primes, because if it had not been 3, 5, 7, but 2, 4, 6, there may not be a solution. Anyway, so that's the Chinese military application, right? Number theory has come a long way since then, and some of the most important recent advances are due to the two Shaw laureates here with us today. Professor Gerd Faltings was born and educated in Germany, and now holds a leading position in the Max Planck Institute for Mathematics in Bonn. The Max Planck Institute is sort of like the National Academy in Germany. It is difficult for me to explain in a simple way his very important contributions. Perhaps I can just say that these contributions include major advances in Diophantine equation. You see the word Diophantine somewhere there. And that is asking whether polynomials, certain polynomials have or have not integer or rational solutions. And I shall also, in the same breath, also introduce Professor Henryk Iwaniak. Professor Iwaniak was born and educated in Poland and now works at Rutgers University in New Jersey. I can try to explain one of his most important results, and that is among all numbers of the form of a square plus a fourth power, x squared plus y fourth. For those of you with good eyesight, you can see that somewhere on the board. Among such numbers, there are infinitely many primes. And this theorem is significant because this class of such numbers is very sparse, very rare. And I hope they will also tell us not only about those results, perhaps, but more so about how they find joy in pursuing these questions. So could I first invite Professor Faltings to come to the stage and speak to us.
Okay, thank you very much for the history lesson. I don't have prepared pictures, but anyway, most information will be verbal, so I try to explain things. So in mathematics, well, the difficulty is that, people are aware that mathematics has something to do with calculating, but this was maybe 200 years ago, and since then people have developed important concepts. And modern mathematics is more about concepts than about calculating. So Diophantine equations are equations dealing with integers. Diophantus was a Greek mathematician, and people don't know when he lived. I think the estimates vary by something like 500 years. Diophantine problems are easy to state to the general public because you just say, for example, you look at Fermat's problem, you want to look whether two nth powers can be the sum of two nth powers can be equal to the third nth power. But on the other hand, if a problem is simple to state, this doesn't mean that it's simple to solve. And in fact, for the Fermat problem, it took all of modern technology to solve it finally in 1994. So what do I mean by technology? So there are mathematical theory and concepts. For example, concepts are the concept of a topological space. So we have things lying around here, and so we want to see how they differ in shape, and we want to have a precise meaning of that. And this is what's today called topology. So we look at things and we allow them to deform them continuously. And for example, we can show that any closed surface, so it doesn't have any holes, is equivalent to a sphere with a number of handles. So we have a sphere, which is just a ball, and we can add one handle, and because we allow this to deform continuously, this is the same as a torus, so like a tire of your bicycle. And then there are spheres with two handles. Well, so this is one. So this is what took some people some time to find out, and also this was done in the middle of the 19th century, and also if one looks at the pioneers, one realizes that you cannot think about anything if you don't have a name for it. So I'm not really in linguistics, but it's clear that sort of they talk about so and so many times connected object and so, but because they have no good terminology, it's difficult for them. So this was one concept, and for me, for the Dirac-Pentan equation, the most important concepts were the so-called algebraic geometry. So algebra usually you think you calculate, so you add numbers, and geometry you think about objects in space like triangles and so. And algebraic geometry, you look at such objects which are given by polynomial equations, and you study them using those polynomials. So the advantage of the theory is that you can introduce ideas from geometry to algebra. So one object in geometry, as I said, for example, if you have a closed surface, it's a sphere with a number of handles, and then, for example, in principle, because you're allowed to deform continuously, you could ask maybe there's some clever way I can deform a sphere with 2 handles into a sphere with 3 handles. But this, but to show that this is not possible, you develop the so-called invariance, something called homology or fundamental groups, and the homology is a vector space. I'm sorry about this. I have to use this associated to such an object, and the dimension of the vector space for a sphere with G handles is 2G. And because 2Gs are different, if 2Gs are different, then also their doubles are different, and so you see that they cannot be deformed. An important, this you can do for topological spaces, but it was important also to do this for algebraic varieties. And for algebraic varieties, it was especially important because you consider them not only over the real numbers, where we usually think about spaces, but over our so-called finite fields, where they are, you can think that they behave similar to real numbers, but you need some precise theory. And this precise theory was developed in the middle of the last century, around 1960 to 70, by Alexander Grothendieck, who was a French mathematician. He had a very interesting life. I don't want to delve into this because I have only limited time, and he also was an interesting character, and he developed the so-called étale topology, and with this one could introduce those invariants. So what I want to say is that, to do things in modern mathematics, you have to learn some theories. And one could say that, a theory is like a subroutine in programming. This means a subroutine is a program which does something for you, and it has the advantage that you don't have to know about the details. You want to do something and you use it. On the other hand, if you really want to cut time, you can get faster by programming all the details in assembler or something like this, but then you would spend all your time on these details and couldn't think about the important thing. So in this sense, you need the theories to make progress. And in fact, in the proof of the Fermat theorem, there were many such theories involved, and so people liked it because it showed that these theories are useful, but some people don't like it. I always get letters which claim that Weil's proof is much too complicated and one has to rediscover the original proof of Fermat. Which I guess, my personal opinion is that Fermat didn't have a proof, because otherwise it would have been found. Yes, one should also make the remark that, to do something new, you need some tool which wasn't available to other people, because our predecessors were not less intelligent than we are. I guess human evolution doesn't work so fast. So we need something like this new theories. So this maybe is a general fact. Then maybe I should say something about my career. So I studied mathematics in Münster, which is a town in Germany. And I met a nice teacher, Professor Nastold. Well, one thing, he told me that you have to study algebraic geometry, which I did. And I also, and his specialty was commutative algebra, which has some relation to algebraic geometry, but wasn't considered rather backward at the time. But I profited from getting a good footing in this theory, and so I graduated in '78. I got a diploma, and then I wanted to go to the US, and I wanted to get a stipend, and with a diploma, the deadline for stipends was already too late, but if you had a PhD, it was easier to get, and so I wrote a fast PhD, and in fact my PhD thesis was not as good as my diploma thesis. So, but I'm still think that it's better to get a fast PhD than to get good grades. And so I went to the US in '78. I spent 1 year at Harvard University. So first of all, I really learned English. I should say in school I wasn't very good at languages because, I'm not good at remembering things which I don't use. And so if you don't speak English, then I forget about it. And on the other hand, I sort of made many new friends there, which, for example, I met Andrew Wiles, who was a young star at Harvard at the time, and so I spent 1 year there, and I went back to Münster, and I became an assistant to Professor Nastold. And there I made the so-called habilitation, which is an advanced degree, and this meant I could apply for jobs. And there was one job at Wuppertal. I wouldn't dare to apply, but somebody from Münster was on the committee, and he didn't promise me the job, but he suggested that I apply. And so I did. I said, well, maybe it's probably improbable that I get the job, but it won't cost me anything. And so I applied, and I was happy to get the job. So suddenly I was a professor, and I should say I was very happy about this, because I guess most scientists at an early stage, they worry whether they can make a living from the science. I mean, I always was a good student, but I knew that being a good student is different from doing good research. And I think, as a student, you learn about the science, but starting with research, you also have to learn how to do new research, and that's a different topic, and it takes some time. So I got this job at Wuppertal, and I was maybe not overwhelmed is the wrong word, but I was lucky. I proved the so-called Model conjecture soon afterwards. So the Model conjecture was an old conjecture which had been made by Model in 1922, and there had been some progress in the 60s. And Professor Nastold had a friend in Paris, Professor Spiro, who had some ideas how to extend this, to make this work even for number fields. But it was clear that the ideas were not sufficient. There was something missing. But I thought I'll think about it. Even if I don't prove the Model conjecture, something interesting will come out. And as a young researcher, anyway, you need some good topic. And so first of all, I proved something about Arakelov theory, which was a tool used there, and I think it's my first really good paper. And then, I looked at this Model conjecture, and then I found out, I guess I was lucky, that you could replace some arguments which didn't work in my case with a so-called theory of p-divisible groups. And so this way I proved the conjecture and everything else, and I suddenly became a star. And so, but then I had to go on. I mean, different from my predecessor, I couldn't retire after this highlight. And so I looked. So there was two developments from the proof of the model conjecture, where I just got my way through by some tricks, and but I saw that you could do a better job, sort of, to polish everything, that it looks much nicer. And so I went on working on this, and it got me some time. So in general, I should say, after proving such a big theorem, I guess everybody's anxious what to do next, because if you have reached one big mountain, this doesn't mean that the other big mountains are any easier, and you cannot expect to sort of continue like this. But my experience is that, you usually find something useful to do, and if you find something useful and complete it, then you are satisfied with your life, even if it doesn't give you so much recognition. And so so one thing with this conjecture, I sort of got maybe famous in Germany. This meant that I first appeared in newspapers, which was unusual. I wasn't used to it, and I was sort of didn't really like the idea that somebody worried about my hobbies. But I've learned that you have to allow for some publicity, as you could see in the videos during the ceremony. But then I decided that I got offers from the all leading US universities, and so I decided this was my chance to go to the US. So I just got also married at the time, and I thought, if you have no children, or if the children are young, you can just go abroad, and this is a good time. And because I already had been to the US, I knew what to get into, and so I got a job at Princeton, and there I got my two daughters, which are sitting somewhere here. You could see them in the video, I think. And I had a happy time at Princeton, and I should also say I had some success at Princeton. At the end, I wrote my second best paper on Diophantine geometry, on Diophantine approximation. This was sort of, it's like the Boy Scout that you should do a good deed. There was Paul Reuter, who had new ideas to give a different proof of model. And everybody talked about it and said how great this was, but nobody seemed to be willing to say that it was correct. And so I thought, I should look at it and check it. And I not only found that it was correct, but also that one could generalize things. And so I wrote my second best paper. So following the Boy Scouts motto is a good idea. After this, of course, I tried to go on with my theory, and I profited very much from Princeton. So for example, I had lectures by Ed Witten on mathematical physics, and my main conclusion was that physics is not mathematics, in the sense that for him certain things were obvious. This was supposed to be the energy, and so on. And then you have to do a path integral, which is, for a mathematician, is an undefined object, and you manipulate it, and you get something. And so I decided, that I can't understand it. I sort of can maybe extract some mathematics from his insight by trying to translate them, but I have no chance of rebuilding physics along my line. So this way I spent time at Princeton. And then my daughters became older, and I heard about others who had, expatriates who had daughters, that if you bring them up, if they become too old, then you refuse to speak your language. They only want to speak English, and you have American daughters. So I decided that it's time to go back. And in between I had gotten the Fields Medal, so it was no problem when I indicated that I had interest in going back to Germany to get an offer from the Max Planck Institute in Bonn. I knew its director anyway, and so in 1994 I moved to Bonn, and I had interesting experience with different school systems, of course, but maybe I don't detail this. And so I'm in Bonn, and I should say I've continued to do research, not on the level of the Model conjecture, but I've always found something interesting to do, and I'm sort of have been satisfied with what I could do. So I think as a scientist you are sort of privileged that you sometimes at the end of the day you can show to something and say, I did this. Well, I guess that's basically my life, and nothing interesting has happened.
Now, may I invite Professor Urania to share with us your ideas and work? Professor Urania, please.
Well, let me reverse my presentation by comparison to Gert. Let me say something first about myself, about how I became a mathematician, and perhaps why I became a mathematician, and then I come back to mathematics to entertain you a little bit with some perplexing problems in number theory. So I was born in Elbląg, industrial city in north central part of Poland, and I think I can say I was fortunate to grow up with my twin brother, who was 8 hours younger. And we were growing together for quite a while until we entered university.
Thank you very much,
in
Professor
1966. There was no really tradition, academic tradition in the family. Nevertheless, my parents really were stimulating by encouragement and by great attention to knowledge, and that was sufficient for us to get interested in science rather early. Not really in mathematics at that time, and so there's no particular incentive to do mathematics in our elementary school. We entered a technical high school in the town, which specialized in, so we learned quite a big deal of machines and technology, particularly about steam turbines for power plants. That was quite an experience which I think had some effect, a trace on my attitudes toward mathematics. For example, I Mathematicians see the beauty in the mathematical statements, but for me it is not enough. You really can see more deeply, intrinsic beauty after you really establish results. So they can see how you got it, the tools, the machinery used is part of the beauty. It's not just a realization of your goal. Anyway, the atmosphere in the high school was fantastic. I mean, there was no competition. Nobody was really claiming to be number one. Some people were good in one field, the other in the other field of interest. How we got interested in mathematics? Well, because of mathematical contests. First in mathematical circle in Gdańsk, and then in mathematical Olympiads, we were successful. So it boosts your ambition. Our teacher couldn't really do much for us, but he distinguished us in the class by excusing us to take tests. So that's also encouraging, something like that. But having a brother, twin brother, it was a wonderful thing to stimulate each other. We could ask questions themselves and look for answers together. By the way, never competing, by the way. We are really never competing. And so went to university, the mathematics department, Warsaw University. But also interesting part of it is that by the regulations of the government, we would not be eligible to enter Warsaw because of we lived far away from Warsaw. So winning the Olympiads gave us this privilege of choosing where to study, also without taking entrance exams, which was a great blessing because I don't think I would pass the mandatory exam in Russian language. Yeah, right. Anyway, and when we entered university, we decided to work in mathematics in a different fields because we wanted to be intellectually independent, which is, in my opinion, extremely natural. When you grow up together as a twin brother, at some point you would like to split. But of course, we exchange our experiences for all the time, and never, ever competed. Right. And I think my brother is as happy as I am getting the show prize. Right, so at the university, I was fortunate that I received attention of Professor Andrzej Schinzel from the academy very early, already at the end of the first undergraduate year, and so I specialized very early. Just makes story short, to say that I already had 2 papers accepted for publication before I graduated, so I never really wrote a PhD thesis in a way because one of these was accepted, and actually, I could get my degree before I got a master's degree, but there was a slight delay because there was a requirement that I have to pass Marxist philosophy, which delayed my defense for 6 months. So I mastered that philosophy in 6 months. Right. Anyway, other interesting episode I would like to mention from that period is the teachers, professors realized that there are a group of good students that would be better if they set a special program for the students, because the regular programs were really too easy. So they created a special group, something like a dozen out of 300 admitted at the time. So we followed from the very beginning a special program. It's an excellent idea. Right. Also, we were really regular guys. We didn't want to be something special. So, but a few of us had an idea of taking exams in advance and pass 1 year and be ahead of our colleagues. But in Poland, and the system so rigid, this very courageous idea required approval of from the dean. But the dean didn't object, but he gave us a wonderful lesson. He said that we are foolish because we are going voluntarily to cut off some of the best years in your life, that is the college years. So we listened to him and we finished on time. Right, yeah. And I say this story sometimes to my students because I think there is no need to be fast or and forget the normal life. We had lots of interesting other things to do, hobbies, and actually it gave me a lot of time to do my beloved subject, number theory, which was not a part of the syllabus. And also I started dating a girl, my wife. And etc. So I think there is no rush for such things, right? And etc. Lots of things from my life could be said maybe another occasion. So let me a little bit say about mathematics. I don't really have time to tell what I'm really doing in number theory, so I have chosen for this presentation something a little bit to entertain, and maybe, but also very perplexing subject that is about ineffectiveness in mathematics. I mean, mathematics is considered as very, very precise science, and it's true, but it doesn't mean that there are no controversy. I'm not talking about something proves we are incomplete. I'm talking about precise arguments which are still controversial. I mean, every statement and hypothesis requires rigorous proofs, as we know. Yet there are some results that are hard to accept, even the rigorous proofs. I have in mind the Banach-Tarski paradox, for example. You can subdivide, a ball, let's say gold ball, into two equal balls. So if it's from gold, then you can improve the budget of the government by doing this. The problem is this paradox. It's ineffective construction using, certain arguments that mathematicians are arguing whether they are accepted or not valid. And in number theory, I jump instantly to this, we have some beautiful examples of ineffective results. And sometimes we would like to accept this as a valid argument, or sometimes not. Yeah. And the best to start would be probably the issue of exceptional character, which we consider as a ghost in the number theory house. It's hard to say for general audience here what it is, but maybe I leave some impression. So it's a character. It's a function chi of n which takes values plus minus 1 according to certain rule, depending on this quadratic residual symbol d over n. And the point is that we don't know exactly, or precisely enough to control the distribution of these values. And there is another function absolutely fundamental for the distribution of prime numbers that's called the Möbius function. And since our knowledge is not perfect, we can see by experiments that for certain discriminants the character mimics or pretends to be the Möbius function. And if it is the reality, if it's not only just just a foolish expectation, then there will be a lot of progress in the theory of prime numbers and the Riemann hypothesis, including also for that, if that such pretentious character does exist. So without explaining what it is, let me just give you some logic behind it. I mean, there are statements in number theory which are proved in 2 steps. One step is assuming that such exceptional character exists, and other statement, the other part is under the assumption that such exceptional character does not exist. So combining both, you have unconditional statement. Unfortunately, there's intrinsic problem here. The result is ineffective, because you don't know which case is the case. And so when you have some implied constants that you would like to make numerical computations, it's impossible. And in some circumstances, such results are really grotesque. I mean, just you see, nothing has been established. But sometimes it does, and not enough time to tell when, but this is something really entertaining and also serious in number theory. I mean, sometimes we wish that this ghost, the exceptional character, does exist, because the consequences for the theory of prime numbers, my beloved subject actually, right, are enormous. You can prove things that are not even capable, that even the Riemann hypothesis is not capable to handle. In spite of the fact that the existence of such character would violate the validity of the Riemann hypothesis, everybody believes in, we do not want to reject, we hesitate to reject the existence of such character because of these consequences. So, and many of these consequences are also related to the distribution of prime numbers. Other great progress that I would like to mention is in Sieve methods. Together with John Friedlander from Toronto, we made some substantial enhancement of the theory of Sieve. Sieve was his old stuff, created more than 100 years ago with the expectation of proving Goldbach conjecture, twin prime conjecture, but this goal was later recognized that not possible to achieve by the fundamental within the fundamental axioms of Sieve method. This was somehow prime numbers were blocked by sort of parity barrier. So we introduced new devices which removed that barrier and opened the door to prime numbers. And got many things about prime numbers. Examples are here, like that prime numbers of m squared plus n to the power 4, already mentioned before, infinitely many of them, is very sparse sequence. His Brown, following similar ideas, got other polynomial two variables representing infinitely often prime numbers, etc., etc. Many of these things. And but the theory of prime numbers is very serious, in my opinion. It uses machinery, but also entertaining. There are open problems which in my opinion, are hopeless to prove. One of these is for example, questioned by Erdős. So I recommend young people to get started and look for it. Gaps between primes can be arbitrarily large, as we know, and also can be bounded by absolute constant. We also know recent results of Zhang and Maynard. But if you take things in 2 dimensions, like on a plane, and to consider so-called Gaussian primes, so that means these black dots in the picture, you have many more directions to maneuver, and you can ask, can you walk to infinity stepping only on Gaussian primes, of course with limited lengths in each step. So this is open question, just for your curiosity, which is, in my opinion, hopeless to touch by current technology. Making mathematics, come back a little bit to this, and learning mathematics offers intellectual joy. But one should really distinguish studying and learning mathematics from doing mathematics research. I recall problems that we were asked to solve during mathematical Olympiads, and retrospectively today when I look back, I said, how could we, young people, solve such hard problems? It's next to impossible. What happened? So psychology aspect matters, because you see, when you are doing tests on contests, you have a certain advantage. You know that the problem is solvable within 3 hours by a clever student in high school. When you do research, and challenge is enormous. You never have a guarantee that the technology available today is good enough to solve the problem. So it's different challenges, and if you succeed to do something like solving old problem, open problem, this is, you may think that in your life, mission accomplished. Something like that. Anything, more comments about that maybe during the conversation questions. So that's all what I would like to say about presentation. Thank you.
Thank you very much, Professor Uraniet. Please take a seat here on the stage. The question and answer section is also about to begin. May I also invite Professor Feltin and Professor Yang to join the discussion.
Thank you both for telling us a bit about the quest for mathematical beauty and truth. Any questions from the audience, especially young people? I will start with one. I mean, we all know what mathematical statements are true. We all know what mathematical statements that are true are hard to prove. But what about the criterion for what mathematical statements or theorems are interesting? Not all hard statements are interesting.
Well, it's a little bit like on the playground. They have to be doable, but not trivial. So like if you climb up, it should be interesting, but it shouldn't be too difficult.
Yeah, I would say too that it's, you have to be some balance. I mean, easy problem is not interesting because you just answer in a few seconds, but impossible problem is boring because you yeah.
But that's only on the difficulty scale. Are there problems which fit on the difficulty scale and yet are not interesting?
Yeah, definitely. Well, I mean, well, you could just sort of ask arbitrary questions. So usually it's interesting because you can do something with the answer.
And also, I think I would add to it that interesting because it fits to greatest, deeper structures somewhere. You know, yeah.
Now, I have a written question here, I think addressed to both of you. It says, mathematicians often work on their own and spend a lot of time in their own work. How would you strike a balance between your work, presumably solitary, and then balance that against your life, your family, and your social life?
Well, one is one thing and the other thing is the other. I mean, well, if you usually you can't work on a mathematical problem all the time, because the usual thing, I mean, most of the time you are stuck, and sort of you work for some time and you are still stuck, and then you should do something else, like talking to your family, or vacuuming your apartment, or doing administration.
Well, I like working together with many people. If you succeed, you get very quickly, satisfaction. But I think the tendency in modern mathematics is to work together in teams in great groups. But if you compare historically with how great mathematicians were working just in solitary conditions, I mean, it's so different than in other. I mean, if you consider mathematics like art, it also differs from other parts of art, like paintings. I don't recall joint painter or musical compositions, yeah. But in science, I think it's very common now. Not only in laboratories, in experimental work, but also in pure thinking. It's also much more common today to work in teams. Also, institutes are created to work in teams. Yeah.
Thank you.
I was previously a math major, and I find out that after going 4 years in pure math, I have developed a habit being a very slow reader. Because if I cannot understand one line, I can't go to the next line. I don't know whether you have that kind of experience.
Well, usually if I read a paper, I look at the statement and try whether I can prove it myself. And then I usually realize what's easy and what's difficult in the proof, and then I understand better why the guy does this or that. So maybe I don't know whether this helps you, but this is my strategy.
One other part of that question, I think, was what to do if you are lost a little bit in reading. I think one could read mathematics in successive approximations. You know, sometimes I have students in the class who are very, very ambitious. They would like to learn hard part, but they're not prepared yet for it. I don't discourage them. I want them to be in the class and say, if you understand 10%, that's a great success. That's something. I mean, you cannot just lower the level of presentation because of few younger, people in the class. And that's my way of learning. Also, when I study myself, some people's work I do by successive approximation. I don't read from A to Z. I just look where is the beautiful things first. Can I capture that? And like Gerd said also, some of the lemmas, technical things, I don't even check. I prefer to prove them myself. But of course, the main line that leads to the final result is due to the author. And so this is my first approximation to understand the paper. But then, of course, sometimes you have obligation when you are referring a paper for the journal to declare that the paper is correct in every aspect, including details that you didn't read. Then it's really a hard labor. Yeah. Yeah.
If I may broadly categorize those who have a PhD degree in mathematics as mathematicians, then there are more and more mathematicians in recent years. Instead of working alone, solving difficult questions, rather end up working for the finance sector. What do you think about this trend?
Okay, I lost few students for mathematical, finances. Went to Wall Street, and smart people go there because they don't really see financial future in mathematics. And it's a pity because I don't think mathematicians should be driven by economical, prosperity. You should first of all love the subject. I would not recommend anybody to go into at least pure mathematics, like number theories, just because you can get a job. I mean, job is, of course, part of our decision-making, where to go and how to behave, etc. But it's not really an aspect that one should really consider as a priority, maybe even completely disregard that, when you do mathematics. Yeah.
So I have no moral reservations if one of my students goes into the financial industry. It's not like going to a house of ill fame or whatever. I mean, it's different well, I guess the financial industry, whether I approve or not what they are doing, it doesn't matter, it just will develop. And, well, okay, I mean, if it gives jobs to mathematicians, the better.
I think we have time for a few more questions. Yes, please.
So I was wondering, do you ever find inspiration for your work outside of mathematics, maybe in art or nature or music? And if so, could you give me an example?
Well, well, the only thing maybe at a film you see that the character overcomes the difficulty and wins at the end. So you can watch Harry Potter or whatever. But for arts, I think I'm not so much versed in arts. But maybe Henry.
Well, I have a roundabout answer to the question. I do find inspiration by doing other things, like a hobby, listening to music, playing a little bit, recently also a little bit of photography, but not directly to get inspiration from mathematics. It's just to be relaxed, to get out of mathematics for a while in order to come back with new, fresh hopes. Yeah.
Thank you.
Could I phrase that question in a slightly different way? I mean, a few generations ago, mathematicians would find inspiration from nature. I mean, you go back to the time of Newton. And even these days, some mathematicians perhaps find inspiration from things like path integrals, which to you are undefined.
Well, I'm not sure whether so many mathematicians found inspiration from nature. I mean, after all, Newton was a physicist, so this is okay for him to find inspiration by nature. And, well, in physics, I mean, it's sometimes, I mean, the procedure is to look what physics, I mean, it's like if you have a statement, you try to prove it yourself, and so similar if the physics people claim something, you try to prove it yourself, and sometimes it's successful. So in this sense, it's inspiration, but I would say, I mean, as a mathematician, you get inspiration from other people sometimes.
Yeah, I can't really add anything to what Gerd said, but again, I would say that inspiration can be by just affected by seeing the beauty, the harmony of the world outside nature, and okay, let me just a little bit change the subject. I would say that beauty and harmony is a confirmation that I mean, in your arguments, mathematical arguments, is a confirmation that you're on good track. Usually when you start doing something by brute force, incomprehensible even for yourself, it's better to stop and and open the fridge and take a beer. Yeah.
I think we have time for perhaps one more question. Do I see any hands? Okay, last question.
Okay, wait. Hello, I'm a PhD student from the mathematics department, and my question is, when I search on some website, I found some mathematicians always work alone, but some other mathematicians work with strong groups. And so my question is, what's the disadvantage and advantage of these two kinds of work style?
Well, if you work alone, then you don't have to wait, you don't have to explain things to somebody else. And if you work with somebody else, you can always think that he will do the work for you.
Other things I would say is that if you work alone, you are not ashamed of wrong ideas. You never tell anybody. But if you work together for decades, as I do, you get rid of these hesitations, and you do sometimes share wrong things. And it's equally entertaining and nice. You just become mathematically married, in a way. You've got your mathematical spouse.
Well, thank you both for a most interesting, delightful conversation about different ways of doing mathematics. And then I think we need to move on. Thank you again very much.
Now we come to the third part of the forum. May I invite Professor Chen Y.Yi, Council Member of the Shaw Prize, to give a brief introduction of the Shaw Prize in Life Science and Medicine, as well as introducing the Shaw Laureates in Life Science and Medicine 2015. Professor Chen, please.
Thank you. So now we come to the third section, or last section of this afternoon's forum. This is on life science and medicine. So we all know bacteria exist everywhere, inside and outside of our body. Some are beneficial and some causes disease. It is well known that even for the disease-causing bacteria, when their number is low, they do not, in fact, lead to any apparent disease or obvious disease. They become pathogenic only when their number reaches a certain level, as if their pathogenic action is coordinated. Bacteria have been regarded as lonely individual cells that act independently from their neighbors. So therefore, it was unknown how do bacteria talk with each other and how can they coordinate their action. So these mysteries were resolved by the work of the two Shaw Laureates in life science and medicine this year, Professor Bonnie Basner and Professor E. Peter Greenberg. Both scientists began their research work on bacteria that produce light-emitting or luminescent molecules. They cracked the secret code of bacterial language. So that bacteria talk with each other and with other species to coordinate functions such as bioluminescence that are difficult or impossible to achieve by individual cells. The strategy with which bacteria talk is called quorum sensing, whereby bacterial cells sense and respond to change in their local densities by the production and sensing of small diffusible molecules. Professor Bonnie L. Basner and Professor E. Peter Greenberg elucidated the molecular mechanism underlying quorum sensing, as well as the implications of the mechanism in controlling bacterial physiology in the context of infectious disease. Professor Bonnie L. Basner was born in Chicago and is currently the Scrip Professor and Chairperson of the Department of Molecular Biology at Princeton University and an investigator of the Howard Hughes Medical Institute, USA. She obtained her bachelor degree from the University of California, Davis, on the West Coast, and her PhD in biochemistry from Johns Hopkins in the East Coast. And then she moved back to La Jolla on the West Coast for her postdoctoral training, and subsequently moved back again to the East Coast to become an assistant professor of Princeton University, where she rose to her current rank. She has been elected to the US National Academy of Science and an American Academy of Arts and Science, and also is a fellow of the Royal Society of London. Now, interestingly, our other laureate, Professor E. Peter Greenberg, moved in the opposite directions through his career. Professor Greenberg was born in New York and is currently professor of microbiology at the University of Washington. He received his university education, the undergrad education from Western Washington University on the East Coast, on the West Coast, and then his master's degree in microbiology from Iowa, University of Iowa, and then his PhD in microbiology from the University of Massachusetts. So moving slowly from the West Coast to the East Coast. And then he slowly moved back from the East Coast, from Harvard and from Cornell, to the University of Iowa, and finally back to the West Coast and joined the faculty of the University of Washington. So similar to Professor Basner, he also has been elected to the US National Academy of Science and the American Academy of Arts and Sciences. So today, Professor Basner and Professor Greenberg will share with us the inspirations that led them to pursue a successful career in scientific research, honored by the Shaw Prize. So let us start with Professor Basner. Professor Basner, please.
So thank you. I'm absolutely delighted to be here, and I'd like to tell you that Pete Greenberg and I are in the same room at the same time. So we landed here. Let's see, it's really fun to be here and to tell you, just give you a few little tastes of what my life has been like. And you just got a very good primer on what we work on, but I'll show you in the first slide what I work on, and then I'll tell you about how I got there. So my lab, all my lab ever thinks about is how do bacteria get any bang for their buck? They are so small. How can it be that they can have so much power on this earth? So they can kill us, as you heard, and we also now know that they keep us alive. And so what we have always wondered are how do these tiny critters do these magical things? And so what we and Pete and others have shown is the way bacteria manage to make a living is by carrying out tasks in groups that they could never accomplish as if they were individuals. And so the way that works is shown on this slide. So this is supposed to be a bacterial cell. So bacteria are small and the world is big. So when bacteria are alone, when they're at low number, they want to carry out behaviors that are good for an individual going solo. So they carry out some tasks, but among the things they do is that they make and release small molecules that you can think of like hormones, but these are their words. So those are represented by the triangles. And so what happens is bacteria are alone and they release these molecules. The molecules float away, the bacteria can't detect them, and that says you're alone. So act as an individual. But as bacteria grow and divide, since all of the cells in the vicinity are making and releasing these molecules, the amount of the molecule outside of the cell increases in proportion to cell number. And so when this molecule hits a particular exact threshold amount, the bacteria detect that that molecule is there, and they infer that they have neighbors around. And so what happens is when they perceive the molecule is present, they say, oh, my brothers and sisters are here, and if we all do things together, we can carry out collective tasks because we're acting as a group. So in synchrony, the bacteria change their behavior and they turn on and off hundreds of genes that specify group behaviors, like virulence. And so it's not that a couple bacteria get in you and they make you sick. What they do is they wait. They count themselves. They recognize if they all launch their attack together, they can make an enormous host sick, or healthy if they're doing beneficial behaviors. And so what we now understand is that bacteria are social, and they talk with chemical words that allow them to understand when they're alone and when they're in a community and what they ought to do in those two situations. And so we know now that this has very important medical implications, but as you just heard, it all started with bioluminescence. So I drew these bacteria in blue because the original observation by Woody Hastings and Ken Nielsen was that all the bacteria turned on light together. And so what was awesome about that is that you could see the light the cells were making. And so that excited scientists because it made the invisible world of bacteria visible. And so then it could be studied. And now we get that probably all bacteria have this capacity, and they turn on all kinds of tasks as groups. But it all started with bioluminescence. And so then that's my science part. And so then what I want to finish or tell you for the rest of the time, so how do you get involved studying that? And for me, the way I started in this field is that I went to college thinking I wanted to be a veterinarian because in my generation, if girls were interested in science, you got sort of coached to become a nurse, possibly a veterinarian, and I loved animals, so I thought, oh, I want to be a veterinarian. So I went to UC Davis, which is a very wonderful veterinarian school in the United States. But when I got there and I got into classes and you had to start cutting animals open and seeing their blood and things like that, I realized I like live animals. And so I was at college and I was only one semester in and I had no plan because I thought, I hate this. And so what I did was I thought, well, maybe I'll try. I was in the biology track, so I thought, well, maybe I'll go to a lab. And so I went to a lab of a professor there that took undergraduates, and they put me at a bench, and they put a pipette in my hand, and then I started to solve mysteries. And these mysteries happened to be about bacteria because that's what this professor worked on. But what was wonderful for me is I loved being at the bench. I loved doing experiments. I loved thinking about the problems. And so I thought, well, when I got to the end of my undergraduate career, I thought, well, I don't want to get a job. I like being at the bench. So I thought I'll go to graduate school because then I can do this for longer. So then I went to Johns Hopkins to go to graduate school, and since I had been working on bacteria, I kept working on bacteria because I was too afraid to work on anything else. It was the only thing that I knew about, so I kept doing that. And so then when I got my PhD, I thought, well, now I definitely don't want a job. It's because I just liked solving mysteries, and I liked making discoveries. And so one of the luckiest things that happened to me while I was in graduate school is that this man, who is named Mike Silverman, who is adverse to following rules, gave a talk that I got to hear. And he's the person that brought molecular biology to that bioluminescence problem. He's the person that cloned the genes, mapped the genes, and figured out what are the components that let bacteria talk to each other on a molecular level. He was the first one to sort of crack the code. And I happened to be in the audience, and I heard this talk that he gave. And back then, we didn't, or at least I didn't think that bacteria were smart enough to have group behaviors. The world thought that bacteria acted as individuals, and only a few people, Pete Greenberg and Mike Silverman being two of those few, people thought bacteria could act in groups. And so he gave this 15-minute talk that opened my eyes. It was all about these glow-in-the-dark bacteria, and I ran up to the podium after his talk, and I begged him to let me be his postdoc, because I liked bacteria and because he told this story of something I had never heard of in my life. And what I think, when I think back on it, it wasn't a strategic move. These bacteria glow in the dark. They're not important industrially. They're not important medically. There was no hint that it was going to be more than these glow-in-the-dark bacteria. But I thought, that is an amazing problem about how all organisms work in groups. And bacteria had to invent that because they're the oldest organisms on Earth. And so he said yes to letting me be his postdoc. He's a geneticist. I was a biochemist. And so I went to his lab in La Jolla and worked elbow to elbow with him for 4 years. And what I would say about him is that you see that he doesn't like convention. So he was kind of out on the fringes, working on stuff that no one cared about and no one was paying attention to. But he was an amazing mentor. And what he taught me is to have fun every single day. We would go in, we would do experiments, we would laugh when we would fail, and we would laugh when we would succeed. And he taught me to be positive about it. He taught me that it is a game, and it's a luxury, and it's lucky. to get to do science, right? We don't make food, we don't make cars, we make ideas. But that is important. Right? He also taught me that there's plenty to discover. I mean, here it is 25 years later, I still work on this glow-in-the-dark bacteria. Like, we will never figure this out, not fully. Right? And so he taught me you never need to compete with anybody because there's so much to figure out. There's plenty for everybody to do. And so the competition is you against that bacterium. And that is the competition I have been in for the rest of those 25 years. He also was really positive with me. When I didn't know what I was doing, I didn't know biochemistry, I didn't know how to clone genes, I couldn't figure out how this bacteria was doing what it was doing, you know, I wasn't thinking about it right, he would always tell me, you're right around the corner, Bonnie, or I know you're gonna get there, Bonnie, or I know you're gonna figure this out. And I believed him, and now I realize as a PI that he didn't have a clue, and he didn't know I was gonna figure any of that out, but I always tell my students, I know you're right around the corner, right? And I know you're clever enough to figure it out. And so he gave me the confidence to just keep going. And so what I would say about him is he always made me feel like I was on the top of the world. And so this is Mike and me on top of the world, right? And so he made me realize that science is a thrill. And I've never lost that feeling, right? I still love to go to work every single day. And the other thing he taught me is that we are the adventurers. We are the Christopher Columbus of this century, right? We know the world is round, right? What we don't know is about this invisible world of molecular components. And so that is where I get my juice. And so I still work on those things, right? So I worked with him for 4 years, and he is still my hero. He's still my mentor. I still think when I write a paper, would this be good? Would Mike think this is good? And it helped me set a bar for myself. And it also taught me how I want to be a mentor, which is to be positive and to make people believe they can do it. And so then after I was a postdoc, Princeton University took a chance on me, and this was long before the quorum sensing field existed. So I wrote 50 applications. I knew, again, I told you I don't have any marketable skills. I didn't really like to work. I only like to be at the bench. And so I wrote all these applications, and I got 2 interviews, right? Because there was no quorum sensing field. But this wonderful university, Princeton University, took a chance on me, and this is me 20 years ago. And you can tell that it's a long time ago by looking at the computer. So I was so excited to have that computer. That was state of the art. So there I am in my office on sort of the second day of work at Princeton. And what I would say is that I was absolutely terrified. Okay, so Princeton's this Ivy League school. I was educated in the public university system. And I thought maybe they made a mistake and they got confused and they accidentally hired me, but they meant to hire somebody else, because I thought, I don't know how to be a professor. All I know how to do is to pipette and to think about bacteria. I don't know how to have people work for me. I don't know how to do any of these things. And so I had what I would call, and it's been called, a terrible imposter syndrome. You know, that I'm a fake. And so I'd be around all these famous older scientists, and I would think everybody here seems to know what they're doing except me. I was like the Wild West. I didn't know what I was doing. They all seemed smart. They all seemed confident. Unlike you, I was not confident, right? And I realized now they were just older. They had been in the game longer, right? And so what I want to do is talk to the young people. I always thought I was the only person who wasn't confident. Everybody else seemed to be. But what I would tell you is that everybody feels that. What's awesome about science is that every stage of your life is different than the last one, and you're never trained for the next one. I was trained to pipette. I wasn't trained to teach. I wasn't trained to train people. I wasn't trained to write a grant. And so all of those things to me were really, really scary. But what I would tell myself would be, what's the worst thing that can happen to you if you fail? You know, you don't die from this if you don't get your grant, right? You still have a job. You just have to try your hardest every day, and that's the best you could do. And so even when I wasn't competent, right, I just loved working in the lab, and students started to come work with me, and I loved the fact that I got to work with smart, curious people who wanted to change the way we think about the world. That's what my days were. And so I would tell myself, you just go in there and do that, even if you fail, because now these young people depend on you, right? And you like working with them. And so over the years, I built my lab. This is my lab just a couple months ago. One of these guys got a job, and so they're at our house having a party. And what I realized is that it's an absolute privilege to live a life of discovery, and that there is no better job than being a scientist, because what you get to do as a scientist is to think about things that no one has ever thought about before, right? And you get to do it with people who like doing that, right? And so it's a real joy. And so I would say to the young people is if you're interested at all in science, even if you're not confident, stick with it, right? Because everybody else isn't confident too, right? And what I would also say, I want to say something especially to the young women in the audience, that not enough of us go into science, right? And that there is a bias. It's just harder for women to succeed. You have to do more to get the same credibility as your male counterparts. That's known. But you don't do this for credibility. You do it because you can't not do it. You do it because you go home and you think about these things at night and you think about it in the shower and you want to make these discoveries, right? And so then you go to work the next day, even if it's a little bit harder because you're a woman. Or I would say, you know, a young person, right? It's hard because people are more successful than you early on in your career. But there's a mechanism for good scientists to succeed. You know, you write papers, you put your product out, and there's a mechanism that great science lasts. And so you don't have to worry if you're not confident, and you don't have to worry if you're a woman and it's a little bit harder, because what happens is there's an infrastructure where if you have good data, it becomes irrefutable. It becomes undeniable, and there's a way to succeed and for the science to drive you to the top. And that's the best thing about scientists, is that we are logical and we do look at data, and good data lasts. And so I just want to encourage, especially the young women to go, and the young men, but especially the young women, to stick with it, because the process and the system will help push you forward. And also, there are plenty of women and men, my age and older, who are there now, and they're looking out for the young people. And we will help you to have these wonderful, joyous careers, because we know that we have had that opportunity. And then the last thing that I would say to the young people is that there's many different combinations that make a winning scientist. You know, there's a stereotype. I remember at Princeton, the stereotype is that you're like Albert Einstein. Okay, so I'm not, right? And so there's lots of different combos. You know, some people like me are not shy, like to give talks. Other people are quieter. Some people are outgoing. Some people like to work in groups. Some people like to work alone. But you can find your way and your path and your adventure. And what's wonderful about science today is that all of those paths are acceptable, right? There isn't one way to do it. And so you can carve out your own project that you love. You can choose people that you like working with. You can choose a style that you like, right? And if you make good findings, the system will push you forward. And you will have the greatest life in the world, because, as Mike Silverman taught me, every day can be fun. So thank you.
Thank you very much, Professor Basler. Now, I would like to invite Professor Greenberg to deliver his presentation.
So, not only am I last to the podium, but as I often have to do, I'm going after Dr. Basler. So it's like the slow dance after the fast dance. But I'll try and keep you amused. I wanted to start with a picture of this famous biologist, Dr. Carrie Harwood. It's my wife and life's partner. So I never imagined that I would be standing here, but she did. And she always had this faith in me. My story is a lot like Bonnie's. I've just enjoyed what I've done every day, and every day that society lets me do it, I feel like it's a bonus. So I wanted to start somewhere early in my life. So I was a horrible, cantankerous student in high school. I drove my teachers crazy. I used to purposely antagonize them because I was so bored. I had a biology teacher when I was about 15 years old who organized an optional field trip going to the ocean to look at things that grew in tide pools. And I signed up for this to his surprise, because all the smart kids signed up, and I signed up too. I signed up because you would get out of class on Friday to go on this field trip. And we saw things like this. This is a picture of some starfish, mussels, sea anemones, all crowded into rocks in a tide pool. I never knew that animals like this existed, and they were in communities. They were organized somehow, and it was a world that I couldn't imagine. And that was the first thing that sparked my intellect. I was really fascinated by this and decided I wanted to become a biologist. I wanted to become a marine biologist. So I woke up and went to college and actually studied, and biology was fascinating. Every minute of biology was fascinating, and not too much else to me, actually. Somewhere along the line in college, I got into the lab like Dr. Bassler did, and I learned that I was an experimentalist, that I didn't really want to go out and study things that lived under rocks for a living. I wanted to be able to tease things apart and design experiments and discover new things. So I decided that that was the direction. And when I was just about to graduate from college, I discovered the world of microbes. And you already heard how wonderful microbes are. We can't exist without them. They make the world go round. They drive the nutrient cycles. At the time, they were the models for us learning how the central dogma worked, how DNA was turned into RNA and into proteins, how life worked. Everything you would want to do, you could do with bacteria, except I was told they weren't social, that they were the example that proved the rule. The smaller things were, the less value there was in sociality. But I decided I wanted to become a microbiologist, and off I went to graduate school. And now I'm going to tell you this story of how I came to the field of quorum sensing. And it starts, I don't know who first said this, but when I read it, I realized it was true of my field. It's been said that every idea in science passes through 3 stages. First, they say it isn't true. Then they say it's true but not important. And finally, they say it's true and important but not new. So it seems like a situation where you can't win. So I'm going to tell you about the stage of bacterial quorum sensing where they say it isn't true. And Bonnie told you about these luminescent bacteria, and she showed you little blue blobs on a cell. This is actually a plate of these bacteria growing up as colonies and making blue light. And they only make this blue light when they're in a crowd, when they're at high population density, like when they're growing in a colony on a plate. And why do they do this? Well, this is one example. So where do these bacteria live? These 2 scientists, Margaret McFall-Nye and Ned Ruby, study this little squid that lives off the coast of Hawaii. And it has a light organ in here in its mantle cavity. This squid you wouldn't find in a Chinese seafood restaurant. It's about this big. And in the mantle cavity, there's an ink sac. You know, squid make ink as a defense mechanism. And surrounding the ink sac is a light organ that's packed with these marine luminescent bacteria. They're in a crowd in the squid, and they make light for the light organ, and the light is shined down into the water column. The squid are nocturnal, so they come out at night and do their behaviors, shining light down so that predators looking up from underneath can't see them because they don't cast a shadow from the moonlight. They're like stealth squid. So the bacteria make light for the squid. It's a mutualistic symbiosis. And the bacteria make light then when they're in a crowd in the light organ. They also live in seawater, but they're not in a crowd in seawater. There'd be no value for their light in seawater. And so they know they're not in the sea. It's time to make light. They're in the squid. And I learned about these bacteria in 1973 when I was a graduate, just starting graduate school. I was still interested in marine biology, and my PhD advisor sent me to the marine biological laboratories in Woods Hole for a special summer course in microbiology so that I could learn more about marine bacteria. And I learned about these luminescent bacteria from this fellow here. Bonnie mentioned his name. This is Ken Nielsen. He worked with Woody Hastings, and they discovered that these luminescent bacteria only make light when they're at high population density. And this is me. And one thing that I did when I learned that I was a recipient of a Shaw Prize was I was sent a DVD of last year's forum, and the laureate in biology and medicine, Peter Walter, showed a picture of himself of this era, which looked pretty much like me, and he said it was a marvel that he managed to catch his wife. You already saw my wife, and I am the luckiest man in the world that she was attracted to this guy in plastic shoes and long hair. So Nielsen told me about how these luminous bacteria only made light at high population density, and I decided that's really interesting. That's something that I think I'm going to work on. And he worked with this fellow here, Woody Hastings. So Nielsen and Hastings did the first experiments. They were physiology experiments. They just grew bacteria in a laboratory culture and then reasoned this whole thing out. And I went to work with Woody after I finished graduate school. So I did my postdoc with him at Harvard. And at that time, he had what he called the autoinducer hypothesis. And pretty much nobody believed him because the autoinducer hypothesis was that these bacteria made some signal, he didn't know what it was, and that when it accumulated, it triggered activation of luminescence genes. And this was really a foreign idea in biology in the late 1970s. So nobody believed it. I figured I can study it. As a postdoc. I hope it's true. If it is, I have a career. And if it's not, I'll move on. And I was also influenced that summer by this guy, Ed Wilson. He's also a Harvard professor, and he studied ants. He studied the social ants, and he had just written a book called Sociobiology, and he claimed that social activity should be in the domain of biologists. This is something we can study as biologists. And so he gave us a lecture at Woods Hole that summer, and I was really taken by that lecture. So I was putting together what he was saying about sociality and what Nielsen and Hastings were saying about these luminescent bacteria, and it seemed to me that the luminescent bacteria were using some form of chemical communication to control this behavior that was cooperative. You can see the light produced by the group, but not light produced by individuals. Another quote, this fellow was also at Woods Hole that summer, Albert St. Georgi. He won the Nobel Prize, I think, in 1937 for finding vitamin C. He said, research is seeing what everyone else has seen and thinking what no one else has thought. And that struck me. What I was doing, I think, was putting together what Hastings and Nielsen had found with Wilson's ideas about sociality. And so nobody believed Hastings and Nielsen. It was heretical. I went to work with Hastings in the late 70s. And in the 80s, we began to learn about the genetics and the biochemistry of this thing that Hastings and Nielsen had discovered. So if you can get genetics and biochemistry, then the geneticists and biochemists believe you. And this is a little diagram from that era that shows sort of a summary of, as Bonnie said, it was my lab and Mike Silverman's lab working on this, and we believed each other. Mike figured out the genetics. We figured out how the signals were made and how the signal receptor responded to the signals. And then we were at the stage where they said, it's true but not important. So what? You know, these funny luminescent bacteria can communicate. Why should we care? And my view is that biology likes good ideas. You know, if these funny luminescent bacteria are doing it, somehow we're going to find that other bacteria are doing it. And so that brings us to the next stage. And in the early 90s, one of my colleagues, I was then at the University of Iowa, had been on a sabbatical in Rochester, New York, working with an expert on Pseudomonas infections of humans. And he came back one weekend, and I happened to be in my office, and he said, you know, we discovered a gene, and when we sequenced it, it looks like the gene for the receptor in your luminescent bacteria. And if you knock out that gene in Pseudomonas, it doesn't cause infections in mice. His name was Charlie Cox. I said, Charlie, that's fantastic. You have to work on it. And he said, well, I'm not really interested in that. I'm interested in iron. And so I had to work on it. And what we discovered is that Pseudomonas uses a system that is very, very similar to the luminescent bacteria. They make these signals, and the signals are made by proteins that look like the protein that makes the signal in the luminescent bacteria, and the receptors look like the proteins that receive the signal in the luminescent bacteria. And this opened up the field. Now it's important, right? Because pathogens are using communication to control their ability to cause an infection. And my world changed then. Mike Silverman and I were no longer the only people working on this system. Lots of people started to work on it. Maybe this helped drive Mike into retirement. I don't know, Bonnie. I kept going because I was young. And so now we're at the point where it's getting a little scary. Because if this is true, then it's time for this. Finally, they say it's true and important, but not new. But fortunately, as signified by the Shaw Prize, we haven't quite gotten to the it's not new anymore. It's still new and exciting, and I think part of the reason it's so exciting is because I have colleagues like Bonnie who can talk up a storm. And so this may be all I have to say. Yeah, so I'll just let Bonnie speak for me, and we'll take questions.
Thank you very much, Professor Greenberg. Please take your seat here on the stage. The question and answer section is about to begin. May I also invite Professor Basler and Professor Chen to be seated on the stage too.
Well, so you have heard two stimulating, inspiring talks. So I think we're open for questions from the floor. Any question? Yes, over there.
You've given examples of quorum sensing among individual types, species of bacteria. Are there cases known where there's communication via quorum sensing that involves multiple species? And if so, does that involve behavior like multicellular or differentiated eukaryotes?
I work on interspecies communication. So it turns out, as Pete showed, there can be more than one molecule, and these molecules in a particular bacterium, and these molecules can encode different pieces of information. And so what we now know is that some molecules are exquisitely species-specific. They say, you're my twin. Other molecules are exquisitely non-species specific. They say, you're not my neighbor. And so the bacteria measure the ratios of those to say how many of me and how many of somebody else, and then they behave differently based on whether they're winning or they're losing in any given consortium. That's what we're thinking about now. And then your second question was actually different. It was about eukaryotes, higher organisms. And so far, quorum sensing has been found in yeast, which is a microbe, but it's more like a human than it is like a bacterium. And I think that's wonderful. The idea is to sort of bootstrap your way up to real higher organisms. But so far, there's quorum sensing in yeast. There's some hints in like bees and ants, that do social behaviors. And so I think that is a matter of time. And that's why it's still going to be important, right? Because I think I think you're going to see that in the next 10 years.
Yeah, I don't have too much to add, but the notion about quorum sensing is a way of thinking about how organisms organize in life. And, I should have mentioned that one thing that really changed the field was when we discovered these signals in Pseudomonas, there were a couple of things that happened, and what had been called autoinduction was now called quorum sensing. We decided to give it a different name, and that sort of caught the imagination of a lot of scientists. And if you think about it, people do quorum sensing. The example that has been used by a science writer friend of mine is if there's a bunch of people in a room and some of them start smoking, if one person is smoking, nothing will happen. But if half the people in a small room in a crowd begin to smoke, then someone will go and open the windows. It's quorum sensing in humans.
Question over there?
I want to ask Professor Bassa a few questions. First of all, thank you so much for being such an amazing role model for young women who aspire to become a scientist. I would like to ask, have you experienced any difficulties in this career just because you're a woman? And do you think the views on women in the science field has changed? And also, lastly, any advice to young women who wants to become a scientist and to overcome any hardships that they may face just because they're women?
So the answer is yes to all of those questions, but it is, I'll just start with the second question. It's changed a lot in the 25 years that I've been in it, right? Women are rising to the top, right? In a biology department like at Princeton, we're 49% women faculty, right? And so it's obvious that it's changing. I'm sitting here. It's obvious that it's changing, right? And so I think that there is still these subtle biases. Like, I don't want to kid you. There's still subtle biases. Like, our grants get knocked down a little bit. It's much harder for women to be the senior author in one of these boutique journals, right? But over time, those things are changing. And what I would say is that the joy of doing science, of making discoveries, far outweighs the remaining biases that exist for women, right? They're there. But if you love science and you want to do it, they become almost just a little bit of noise, and you just learn to accept that that's sort of the world that I live in right now. And then you also hope that if you keep at it, maybe it's easier for the next generation, right? And I think that will be true for your generation, because I think lots of men and lots of women realize that when science gets really good is when all kinds of different people are in the fray. And so I mean genders, I mean nationalities, right? That's when science works best, is when people of different perspectives, it's quorum sensing, get together and then everybody gets more. And so I think that you can bank on that, right? And I also think that yeah, that's what I would say, that it's changing a lot, it's changed a lot, and that it's, even if, every job, has parts of it that aren't perfect, right? But the parts of being a scientist that are perfect are so much more.
Over there.
Okay, thank you. So my question is about your direction of research. Since we're very privileged to see your research in terms of quorum sensing. So, to what extent were you, for example, when you fully see the mechanisms of these kind of things, to what extent will you stop and move on to a new field? And how can you find the connections during your whole research career? You will have research in several fields. So how can you find a connection, and how can you move on? Yeah, that's my question. Thank you very much.
You want me to go first? Yeah. Okay. So for me, it's been a sort of a evolution to a point where I can begin to ask the questions that I always wanted to in the beginning. Remember, I told you that what interested me was this idea that bacteria could communicate so that they could coordinate cooperation. And in order to really study that, then first we had to prove that there were genetics involved, what the signals were, what the receptors were, what genes were being controlled by quorum sensing. In Pseudomonas, there's 300 genes being controlled by quorum sensing. What other factors were impinging on whether quorum sensing was activating genes or not? And this all took, there was a decade of working with just Mike Silverman's lab to figure this out in luminescent bacteria, another decade where it exploded, and we found that it was happening in all kinds of bacteria, and we figured out how the signals were synthesized, things that could break the signals down. And now we're to the point where, for me, we're having an absolute blast in the lab doing what I call social engineering experiments. So we can predict what should happen under certain situations. If we make a situation where quorum sensing is absolutely required for the bacteria to succeed, will there be mutants that come up in the population that are freeloading, that don't do quorum sensing, but benefit from the cooperation of all the others? And we can set up systems like that. And the more we learn about that, I think the more we can think about new ways to control diseases in the future. So this is the direction of our basic research, understanding how quorum sensing is actually controlling sociality in groups of bacteria and how we can manipulate that control. There's also a big practical side of the field that's come up that both Bonnie and I and hundreds of other labs are involved in now. Can we control diseases of plants and humans by somehow manipulating whether the bacteria can sense the signal that their neighbors are producing? So this is the direction, these are the two directions that my lab is going in. It's moving as we gain more knowledge, then we can ask more sophisticated questions.
And I'll just add a little bit. I think you're asking, how do you know what your next question is, right? And so the bacteria tell you your next question, right? So like when we found this interspecies molecule, we thought, now they can talk between species. And so then we said, well, I wonder, can they talk across kingdoms, right? So it's an obvious next extension, right? And so then we started to go hunting for those molecules, right? And then like once we found one bacterium that eats the other guy's signal, and so it makes the guy miscount. And we thought, can we do that? And that's how we got into this idea, like maybe we could manipulate it deliberately to make medicines, right? And so I think that one thing that happens is every time a scientist gets a result, you're so happy for like an instant. You're like, I have been looking for, you're trying to find this molecule. I'm so happy. And then you like 2 minutes later, 2 minutes later, you say, well, why do they do that? You know, and then you sort of get your next question. And then I would say another thing that I always do in my lab is that when students come and they talk to me and they say, I want to ask, you know, this. What we actually overtly do, we say, if we figured out the answer to that question, would it fundamentally change our understanding? And if the answer is no, you know, like we would know a detail or we'd know a little thing, then we don't do it. And that is something we ask ourselves every day. Does it matter if I do this experiment? Because if I knew the answer and I'm not very far ahead from where I am today, somebody else can do it. And that's how I run my lab.
Yeah, I'll just add a little bit to Bonnie now. Of course, I run my lab the same way. And we always ask whether that's incremental. We don't want to do incremental science. And I always tell the people in my lab that if you think like that, it's not so hard. I mean, it's not that easy, but there's lots of people that are doing the incremental science, and you can rise above the fray by just asking that question that Bonnie just asked. If you find out the answer, has it moved anything?
Yes, over there, right in the middle.
Thank you, and allow me to ask something more technical. I was wondering about the interspecies quorum sensing thing. Like, are there occasions like some species try to hide themselves? I just heard Professor Butler said about how some may eat up other signals. Would you mind elaborating on that?
Sure, a little bit. Yeah, so lots of scientists work on this, including both of us in our field. And so again, right, so now the scientists have this idea, oh, maybe we could manipulate quorum sensing and make bad bacteria stop talking, make good bacteria talk better. And then you think, well, maybe the bacteria already thought about that. They had a 4 billion year head start, right? And so in fact, lots of scientists have gone out, and sure enough, you know, bacteria that live in fierce competition with each other, you know, are trying to trick each other. So there's some bacteria that eat the other guy's autoinducer, and then that poor guy can't count. There's bacteria that make autoinducer inhibitors, you know, to presumably stop your competitor from counting. There's some bacteria that make the molecules like Pete showed, and there's a guy that will be like next to you in the dirt that makes an enzyme that cuts the ring off the chain, so the one guy's trying to talk, and the next guy makes you mute. Right, so they free ride, they cheat, they eavesdrop, they respond to their signals, and so all of those games exist out there. And now what the scientists are trying to do is to bring those into the lab, the naturally existing pro and anti-quorum sensing strategies, and say, look, if those exist in nature, they won over 4 billion years of testing. We, the scientists, should use those as the building blocks to try to make products based on what the bacteria already invented. So there's many, many increasingly numbers of examples of those kinds of interactions. And I think it's a really profitable part of our field.
Yeah, I don't want to get too technical, but I want to give you one example that we've sort of discovered in the last few years. So we know, we've learned a lot about these acyl HSL quorum sensing signals that I showed you, and all of the bacteria that we knew about until 2 years ago made a certain concentration of the signal, and it takes a certain concentration for them to respond. There were some bacteria, particularly important bacteria that interact with plants, that we knew had the genes for quorum sensing, but whenever people looked, they could never find the signal. And finally, a couple people in my lab somehow figured out that's because they're making signal at 1,000 times lower concentration, so everybody was missing it. And their receptor can sense their signal at 1,000 times lower concentration than it senses than other bacteria sense. And their receptor can also sense the concentrations of signal that other bacteria make. So these bacteria can eavesdrop on other bacteria, and the signal that they make is way under the radar of other bacteria, so no one can see their signal because everyone else is tuned to see a higher concentration. So they're eavesdropping and they're under the radar of everybody else. And this is a new area that's just developing now.
So because of time, we can have two more questions. So one at the back, very back, yeah.
Professors, thank you for your talk. Along the journey, have you ever come across some obstacles? And like, of course there is, like this long journey of research. How do you tackle these obstacles to move forward?
Yeah, I mean, so as I think both Pete and I told you, right, the first, let's say, 20 years of this, right, people thought first that it was crazy that bacteria could communicate, right? That was thought to be the purview of higher organisms because there was a snobbery that bacteria were primitive and dumb, right? And then after that, it was restricted to these glow-in-the-dark bacteria, so even if they could communicate, they weren't medically important, right? And so I think that one way to so it was hard for us to get grants. You know, it was hard. There was a lot of obstacles in that, right? It was hard to attract the best people to work with you, right? But one way to get over those things is to say to yourself, I know that I am working on something that is fundamentally important. It is important to understand how on Earth organisms learned or evolved to do collective behaviors, right? I know group behaviors work. Are here, right? And so if you just tell yourself in your heart, this is a really important problem, it helps you to keep going. And then the other thing is that the people that do come to work with you, because you're on the fringe, they tend to be the most creative, risk-taking, adventurous kind of scientists. So they tend to not ask incremental questions because they were brave enough to come work with you, right? When you're working on something that the world thinks is kind of maybe a fringe problem, right? And so then again, with enough time and enough papers, you know, getting out there, as I said, it becomes undeniable that we're right, right? And then everybody comes and works on it, right? And so I think that you just have to have a steadfastness, and you have to love what you do, right? And know that you just believe it's important to keep going. At least for me, that's how I kept going.
Yeah, I think you heard from all the laureates today that what we do is just deal with obstacles. And we like to do that. You know, so as long as someone will let us keep trying, we'll keep trying. And I was fully prepared all through my career for someone to say, that's it, you can't keep trying anymore. Then I'll go do something else. But fortunately, I get to keep going.
Well, I think this is, do we have time for one more question?
Yes.
One more, okay, the last question, over there. Sorry, over there. Oh. Well, why don't we have the last one? The one at the back. The one at the back, yes. Sorry.
Here you are.
I want to ask, as biochemists, do you have to do any field research? And if so, how does that come in with your lab work, and how do those two components come together?
Okay, Bonnie's looking at me because she knows that we both like being in the lab, and she knows that I learned the harder way. So when I was a postdoc, I decided I would try field work. I would go on oceanographic expeditions and hunt for luminous bacteria. And that was fun and sort of interesting, and we found lots of luminous bacteria. But for me personally, it was not satisfying. You know, it takes an immense amount of work to prepare to go on an oceanographic expedition. You get out there, you get in a storm and you can't do anything and all your glassware breaks. And then you get to answer little questions. It's hard. And in the lab, you can do these fantastic things. You can have huge populations of bacteria that you can manipulate any way you want. So I made the decision. It's not that I don't like going out into the field, but that's my hobby. I showed you a picture of my wife. A vacation for us is going to the ocean where we can muck around in tide pools. It's amazing, but it's not going to be what I do for my life's work.
Well, so with that, let us thank our laureates for the most inspiring and interesting.
Thank you very much. Please return to your seats on the floor. Thank you, professors, for sharing your experience in doing science. Meet the Shaw Laureates 2015 Popular Science Forum is now concluded. We are appreciative for the professors sharing with us and joining in this event. Thank you.